I also wanted to thank the organizer for allowing me to speak at this wonderful conference. It's been great. I'm not audible, is it? Okay. There's a precise angle I have to move. Okay, thanks. Right, so maybe to start off, I should give a bit of disclaimer that somehow the topic is a bit outside of the scope of interest for most of the audience here, perhaps. But I hope to convince you that, well, here are some important arithmetic geometry constructions which benefit remarkably from the theoretic and combinatorial point of view. Yeah. So to start off, let's look at this affine curve cut out by this equation. I don't know how to point. Okay. So this is an action of SL to FQ, the finite group, by just matrix multiplication. And also you can scale by Q plus first roots of unity. It's stable under both of these actions. And if you are Drinfeld, when Drinfeld was 19, he realized that you can take a homology, Ital homology of this curve, and you can realize all the irreducible Caspidal representations of SL to FQ this way. Right? So you take the isotopic component, fixing the character of the right-hand side group to create a representation of the left-hand side group. But of course, maybe for small ranks, you can just mess around with the character table to figure out what the representations are. But it doesn't quite work that way for higher rank group. So in a landmark paper of Deligne-Lusztig, they came up with the idea how this generalizes. So the way it goes through, I'm going to borrow notations from Evgeny's talk, left and right. So for a finite group of D type, for any element in the finite while group, you construct this subvariety of the flag variety, G mod B. It's the set of points in G mod B that, that has the fixed relative position given by W with its Frobenius translate. And in case it looks like a big jump from the previous equation, maybe you can just compute this matrix equality and then look at the left-hand side entry, which indeed recovers this equation. Right? So indeed it generalizes, and the big theorem was that this is how you can construct all the irreducible representations of finite Chevalier groups. For us, however, I just want to point out some of the important geometric output of this construction. To begin with, this is always non-empty because this Lang map is surjective, which also incidentally explains why, I could have tried to make it a bit more complicated and introduce an additional group element here in between G inverse of sigma G, but it wouldn't make a difference because you can always conjugate that, sigma conjugate that to the element 1. And that essentially says that even if you introduce an element here, it's going to be isomorphic as a variety to this XW. Okay, so it's also a smooth and equidimensional of expected dimension given by the length of W. W naught is a Cox-Zetter group, so there is a notion of Buhat order and length. And also there is a clean criteria of when it is irreducible. And using this criteria, you can also figure out, well, if it is not irreducible, how many irreducible components there are, so on and so forth. Right? So let's step into the affine world, where, well, we can make some straightforward generalizations. So let's start with, yes, it's indeed the inverse image of the Schubert cell under the Lang map, right? It's the inverse image of the Schubert cell, BWB, under this Lang map. So just by the definition itself. Now, are you asking that how is it compared to? Right, so you have to make this question with the same dimension even, right? So, okay, you have to make this question precise. I guess one thing you could ask is that in the homology of flag variety, I can take the classes given by these Schubert cells and also by these Deligne-Lusztig varieties. What is the basis change matrix? There is a worked out answer to that, for example. Yeah, thanks. Right, so as I was saying, so let's step into the world of affine Deligne-Lusztig varieties. And maybe the disclaimer is that this does not quantify Deligne-Lusztig varieties that are affine. Yeah. What, sorry? The closure of Deligne-Lusztig variety, you're going to get smaller level. Right. I mean, not G mod B, right? You're just going to get smaller level Deligne-Lusztig. It's just like the Buhat cell. Yeah, it's the same Buhat order situation. Yeah, thanks. Right, so okay, we start with changing the field, and then if River is the maximal unidentified extension completed, And then the Frobenius from the finite field can be lifted upstairs. You also fix a sigma stable Yahori subgroup, which, for example, if we are in the case of GLN, this is the analog of Borel subgroup, right? So it's the inverse image of the Borel under P maps to 0. And with this data, we can define the affine Weil group, or rather the Yahori Weil group, which is an affine generalization of just the Weil group, right? So it's the semi-direct product with the co-character lattice of the finite Weil group, and the sigma that was lifted upstairs, it acts on each of these things. It acts on the group and similarly goes for the affine Weil group. So now using this, so to define this affine Deligne-Lusztig varieties, we have two different kinds of decomposition on the loop group. One uses the index set as this affine Weil group. So this is just the affine Bruhat decomposition. We can also look into the sigma conjugacy action. So sigma conjugacy is just, you say that G1 is conjugate to G2 if there is some H such that G1 is H, H inverse G2 sigma H. Right? So it's an equivalence relation, and you just partition your group with respect to this. And the index that I'm just calling it BG. So the affine Deligne-Lusztig variety tries to understand the interaction between these two different decompositions. Both are stratifications because they also have the usual orders and they are strong stratifications. So in the affine flag level, yes, B of G is just the placeholder index set. So it's just the set of sigma conjugacy classes in GFREB, which we are going to see soon what it is in a more concrete terms, maybe. So okay, so then given a parameter W and B, one coming from each of these decomposition, one defines sort of this locally closed subvariety of the affine flag variety, whose geometric points are given by the equation that we kind of saw in the last slide. But here's one important distinction, that B is non-trivial, unlike in the previous case. So our finite field, there is the lag map is surjective, so it doesn't make a difference if you introduce a B. This fails over FPT. So indeed, you're going to get different kinds of varieties. However, you have a bit of freedom, so you can choose to replace B by a sigma conjugate of B, and you're going to get an isomorphic variety, which is why I'm collecting these things in BG. Okay, so that looks like a straightforward generalization, but somehow for my interest, the object of importance is this seemingly mysterious union over a finite subset of the affine Weil group, right? So this is the so-called admissible union. So what is this? It's just given by some Bruhat order inequality. I'm just collecting certain W's. So given the data of mu and B, mu is a co-character and B is an element in the group, I'm just looking at all the elements in the affine Weil group that are smaller than a finite Weil group conjugate of T mu, the transition mu. So I'm just using this decomposition of W tilde. Yeah. Okay, so just to say something that somehow you can, of course, generalize this in certain ways. For one, you can allow different parahoric level structures. So one important parahoric level structure is the hyperspecial level, which for GLN, we can think that this hyperspecial level subgroup is just GLN with the ring of integers. Entries coming from the ring of integers. And then one can define this X mu B, which is different from this X mu B. This lives inside affine Grassmannian. And for the studies in this world, somehow this is the easiest line of entry. And we often have better understanding of how the questions are solved in this level. And then that sort of gives you a rough guideline of what you can expect in the affine flag. But then those are mostly open-ended questions. So we still try to approach it, being guided by what we know about this one. And also we can change the field to allow for mixed characteristic situation. In this case, we have to allow for perfect schemes. But in that case, the scheme structure is known by work of Bart, Schulze, and June. So yeah, just to say something about why we care about the union. So the reason is that it comes in the context of Shimura variety. So to give a broad overview of what it is, so you start with a Shimura datum, so a group G over a reductive group G over Q and some Hermitian symmetric domain that satisfies a bunch of properties. And you have a parahoric subgroup like the one that we saw in the last slide, perhaps. And then you construct certain double coset spaces. These are complex quasi-projective varieties, but turns out they're defined over a number field. And now, once you have something over a number field, you could ask whether there is an integral model. This involves deep work of Kissin and Papazhou, who proves that there are certain integral models depending on certain conditions that you impose on the Shimura datum. And once you have something like that, you can take a special fiber. So the special fiber decomposes into certain pieces, certain locally closed subvarieties. For the modular curve case, which is the easiest Shimura variety associated to the group GL2, the modular curve is a parametrizing family. It parameterizes elliptic curves. And for the elliptic curve, so if you take the special fiber, we're really trying to understand elliptic curves over FP bar. They can be either ordinary or supersingular. So this Newton stratification is just a generalization of this kind of distinction, right? And then it turns out that actually each of these Newton strata can be further decomposed into two simpler to understand pieces. So locally around every point, you can sort of have this conjecturally affine piece, and then this formal scheme. And this union that we saw in the last slide turns out to be just the underlying scheme of this formal scheme. So a lot of topological information, therefore, of this piece is captured by that union in the last slide, which is why we care about that certain union. And of course, this generalizes if you put a paraholic level structure somewhere, we get a similar kind of union of ADLVs. Okay, so just to sort of state what are the problems that we care about in this field is, to begin with, what is a surprising question, but still not fully resolved, is that when is this non-empty? Okay. Remember, we said that in the finite field case, this question makes no sense because the Lang map is surjective. Everything is non-empty. But in this case, this fails. So this is a non-trivial question. And then if it is non-empty, you want to understand the dimension of this variety. You want to describe its irreducible or connected components. And going beyond that, you want to understand if there's a simple criteria through which we can understand this. And this kind of questions and their resolution has had impact. As you can see, some conjectures there. And well, let's try to answer this question to understand a bit about what we know in the affine Grassmannian case. As I said, that this is somehow the more tractable situation. So to just say what the kind of answers are, this BG set has a neat classification by Kottwitz in terms of two invariants. So one lands inside the fundamental group of your group, the Galois invariant, and then the other one is some co-character, so dominant rational co-character. And then well, this is somehow the sort of broad overview of the kind of answer that we have had in the last 20 years. We can understand the non-emptiness pattern in terms of a dominance order inequality. Then there was a resolution of the Rappaport's conjecture on what kind of dimension they should have. And then also, this one is perhaps interesting. This was more recent, as you can see. So there are so many names, I could not write the names. I just have to abbreviate. But the year is perhaps important. So this was only conjectured in 2017, and it was resolved by 22. So X mu B is not quasi-compact. It has infinitely many irreducible component in general. But this GBF is just the sigma centralizer of B. It acts on X mu B. And this action is like a variety morphism. It preserves the irreducible component dimension. So this it top is just the top dimensional irreducible components. And you could ask that, well, and it turns out that this is a finite set. You could ask that what is the cardinality of this? Turns out that this set has some kind of crystal structure, right? And you can see indeed that on a numerical level, that is a weight space. So here Newton B, then there is a floor function. So Newton B, remember, is supposed to be some rational co-character. This floor function is sort of just creating an integral co-character. And this is smaller than mu, so taking this weight space makes sense and so on. So somehow these are our blueprints, and we try to understand what the answer is in the affine flag level, which differs drastically. So instead of telling you what the answers are, I'll just give some quick examples. Yeah. Mu diamond, right, it's a Galois average of mu. So sigma had an action on this co-character lattice and in the Galois average. So in the affine flag, maybe instead of trying to tell you much more about the theory because I'm running out of time. So there are different ways we try to understand this, but one prominent way is this Deligne-Lusztig reduction algorithm, which was adapted in the affine case by her, taken from Lustig's original work. So somehow the idea is this, that we want to understand XWB. So there are two pieces, W and B, and those are both coming from some combinatorial skeleton. Well, maybe if we can try to understand this W, maybe we can reduce the combinatorial complexity of W by going down in length. So this is describing a certain algorithm where the left and the right children, so you basically try to see that if I can conjugate this element by a finite simple reflection, not finite, simple reflection, to go down in length. If you can, then this one is just recording the left child, SW, and this one is the conjugate, SWS. And you just do this thing. So the theorem is, it's really easy to understand what is the affine Deligne-Lusztig variety for a minimal length element in a conjugacy class. And then you have to somehow keep track of how we can go down to these minimal length elements. Right? And if you do something like this, perhaps you can fill out these tables. What is this picture? This, you can see some alcoves here. So each of these alcoves, each of these triangles are just encoding some element W in the affine Weil group. I chose a particular B. This admissible set here has 13 elements. So it has 13 alcoves in this shaded area. And each of these alcoves are either gray or white. If it is white, that means the corresponding W gives you empty affine Deligne-Lusztig variety. If it is non-empty, then there is a number written here that you cannot see, perhaps, but it's the dimension of that affine Deligne-Lusztig variety. And you can get both of this kind of information from, for example, running this kind of algorithms, which are very easily computer implementable. Okay, let me try to come to the union. So as we said that for affine Grassmannian, we know this answer by 20 years of work. For affine flag, things seem arbitrary and weird. However, the union seems to behave better. And there is, of course, good reason, because the union is what comes from deep geometric structure. So hopefully it should behave better. Indeed, for the union, we do have an understanding of when this is non-empty. In fact, it's the same measure inequality that we saw earlier in the affine Grassmannian case. The dimension formula is rather mysterious, and we know it for some recent work, including some work of mine. We know it under some generosity assumptions, but those assumptions immediately preclude them coming from some Shimura variety. In particular, they enforce that mu should be regular. And if you're coming from a Shimura variety perspective, mu has to be minuscule. But okay, there's some first approximation to whatever the final answer is. But perhaps more importantly, you want to understand, going beyond the numerical values, that, well, what kind of structure do these varieties have? And this is interesting, because once you know a good structure of this x mu b's, you can use that previous framework of Shimura variety, and you can try to understand the cohomology of each of those Newton strata. And understanding the structure of x mu b would help you to explicate whatever that is. So starting with the work of Vollard and Weidhorn back in 2009, this has been observed that often enough. So remember, I told you that BG has a partial order. So the non-empty, the subset of BG that gives you non-empty union, they are called BG mu over here, the notation. And this is the partial order. So here I'm just drawing out whatever this BG mu is, starting with mu to be the second fundamental co-character. And the arrow goes from larger to smaller, right? So it has often been observed for the smallest element, this union seems to be stratified by some classical Deligne-Lusztig variety. And it has been classified when that exactly happens, right? So we don't understand all the strata. We know quite a bit about what is the minimal strata. What does that look like? So that could naturally lead to the question, let's try to understand the maximal strata, right? So that's where my work comes in. So here we give some dimension formula of whatever this maximal, the ADLV corresponding to the maximal strata is. Here G star is the quasi-split inner form of G, and this is the split rank of the semi-simple split rank. And this is some error term which is explicitly described. And then similarly, we have a Chen-Zhu conjecture type of answer for whatever this is. And here is some finite Weil group. It's a subset of some finite Weil group. Okay. And then we can also give an algorithm that generates the lower dimensional irreducible components. In fact, it's the same algorithm I showed you a picture for. The claim is that you can perform that algorithm on the top dimensional element, and all the irreducible components that you get in your affine Deligne-Lusztig variety just comes from those. Okay. So here is some more precise version, but I'm running out of time, so let me skip over. This is supposed to be somehow correspond to this over here, but it's okay. So this epsilon mu, so to speak, here, it's some cardinality of some explicitly described subset of simple relative roots. So what is that? Well, it's just the intersection of the stabilizer of mu with whatever we are seeing here. For the non-split, non-quasi-split groups, that's somehow the table that captures this information. So to say a bit about what is the kind of technique that we are using here, so I want to emphasize one aspect, one ingredient that goes into proving this kind of theorem, which somehow comes surprisingly from the theory of quantum Bruhat graph. Now, this is the sort of combinatorial skeleton that appears in quantum Schubert calculus, where you want to understand the structure constants of quantum Schubert classes. And so what is this? It's just the Bruhat graph. So the finite Weil group elements gives you the vertices. You have the upward edges that just comes from the Bruhat order. And now you have some downward edges, right? So these are 6 elements in S3. This is identity. This is the long element. So the downward edges just correspond to the fact that if you multiply by a reflection, not necessarily simple, you're supposed to go down in length as much as you can. Okay. So it was by some earlier of a Postnikov with his collaborators that shows that, well, this is a connected graph. You can go from any element to another, right? And you can have multiple ways to do so. But turns out that all the shortest paths connecting them have the same weight. So here weight of a path is just the sum of the weights that appears along the edges. So that gives you a weight function that takes as input a tuple of elements in finite while group, and it outputs some coroot, positive combination of coroots. So why is it interesting in our context is that, well, for example, it actually allows you to pin down whatever this maximal element is. Okay? So this maximal element, here's something going on here, but this maximal element is just sort of being taken, it's the maximum over another maximum. Okay, so it's the maximum over admissible set, and then in each of those Brouillard cells, you have a maximal sigma conjugacy class. So now somehow, at least on a surface level, it would be good to get a combinatorial understanding of each of these two pieces. Okay, so I want to understand what is admissible mu in terms of sub-description that is amenable to our consideration. And I also want to understand whatever this is. And those are the two works that was achieved recently in increasing degrees of generality, which actually, so as if you just look at the formulas, you'll see that there is this weight function that shows up in each of these formulas, right? So somehow that tells you, okay, your job is at least somewhat done in the sense that we know at least we have to take a max. We have to take a max over three things actually, in some sense here, which tells you therefore what is this maximal element B max. But of course, that's one part of it, and then you have to understand whatever each of these DLVs are. So that's one aspect of how this proof goes. In fact, it proves for you the first part over here. Okay. So let me go rather to an application of this. So somehow I tried to give an impression that, well, in affine Grassmannian, we know quite a bit. And that also makes sense because affine Grassmannian, the ADLVs and affine Grassmannian, they're corresponding to Shimura varieties that have a good reduction. So the special fiber is smooth. So the geometry is nice, therefore the combinatorics is also nice. In the affine flag, the combinatorics is intricate because it somehow has this Coxeter group combinatorics going on. And that is mirrored by the fact that the Shimura variety correspondingly has a bad reduction, right? So the singularities are bad, therefore the combinatorics is also kind of helpless. In particular, as I said, that we do not have a good dimension formula for this x mu v's. But maybe one could be hopeful and ask, well, can I at least classify when this is zero dimensional, right? Just a bunch of points. So this was achieved early on by Vyjayanthi, where, well, this is the group theoretic datum. So this says that you have GLN and the first fundamental co-character, or it's a restriction of scalar along some finite unramified restriction extension. Okay, so in these cases, you get zero-dimensional ADLVs in the hyperspecial level and in the affine flag level. And this was achieved because we knew an explicit dimension formula of this guy. So you sort of set it equal to 0, and then you do something with it. However, in the affine flag, we do not have a dimension formula, right? So we have some approximation to whatever this is. And those formulas are helpless in trying to understand when this is zero-dimensional. However, there are, of course, certain rigid structure in this Newton stratification. In particular, there's this purity phenomena that helps you connect a Newton strata to the maximal Newton strata, right? So it says that the codimension of any strata in its closure is at most 1. And you can sort of start with a B, and then you can go up to B max, and you can sort of bound that by above by the length of how long it takes to go upstairs. So now that I have this formula, and we have an understanding of this purity phenomena, one could try to therefore turn it into an inequality like this, right? So the first part comes from this purity phenomena, and the second part is what I computed earlier. And if you sort of plug it in, this term I have not defined, but it's easy to write down whatever it is. It sort of gives you an inequality of this form, okay? And of course, this could be useful to find. We do not have an equality for whatever this dimension is, but I just want to know when this is 0. So if this is 0, that forces the right-hand side to be 0. Each of these terms are positive. So that tells you immediately G has to be quasi-split because this term has to vanish, and this guy has to be 0. These are rigid constraints on a zero dimensionality, right? So you can use this. There is another way that things could be zero dimensional. So this Hodge-Newton decomposition, so to speak, which basically, roughly speaking, allows you to break an ADLV into a bunch of pieces one associated to the semi-standard Levy subgroups, if certain conditions hold. So you also have to apply this trick to each of those pieces. And somehow if you combine them together, it tells you that indeed, in the affine flag variety case, this dimension is 0 if and only if, perhaps after you apply this so-called Hodge-Newton decomposition, you get this extended Lubin-Tate type. So it's a finite restriction of finite undefined extension of GLN with the first fundamental co-character. And this was achieved with some more combinatorially technical analysis in a work from last year, but this can be achieved much more efficiently through this work. And my time is over. Thank you.
Are there any questions?
Presentation theoretic question like.
Right. So, well, the result itself, as I said, that somehow the overarching goal is that we're trying to understand each of these Newton stratum, right? And then the Langner's correspondence tries to understand the cohomology of this guy. And this stratification tells you that's the sum of cohomology of these things. And somehow then you have to make precise what is this tilde situation going on here. But at least it tells you that, well, if you pass to, maybe you have to change the local system and so on and so forth. But the cohomology of this piece with the local system is going to be a product of these two things, corresponding cohomologies. Yeah. Now this has limited utility from what I am doing because the cohomology does not depend, like cohomology of a formal scheme cannot be detected from just the scheme itself. But at least the dimension tells you that in which degrees they can occur. Right? So there is this framework of Kottwitz conjecture that exactly tries to understand this question. You want to understand what is the cohomology of each of these Newton stratum. And this has been proved in certain degrees of generality. But the input to that conjecture is that now that I have a dimension formula, I at least know which degree to look at. And I have an explicit understanding of what the reduced scheme is. So that could be useful to figure out some of the cycles in that cohomology. So this has been used, the similar kind of mechanism has been used, for example, in, as I said, this the Tate conjecture on Shimura varieties, certain Shimura varieties. So in those cases, the description of irreducible component for the minimal element B was used to understand the special cycles of the corresponding Shimura variety. So yeah, so in terms of application, somehow the idea is therefore that it helps you to understand the cohomology of each of these individual pieces, but that needs work. It's an expected guideline that has to be carried out with non-trivial geometric inputs. Yeah.
Any other questions? If not,